In this clip, we want to discuss a topological notion, a notion that is not of calculus nature, which is the notion of simply connected domains. The relation to our course in calculus is going to be regarding conservative fields, but we're going to discuss that a bit later. So here we're just discussing the topological notion itself. So what is a simply connected domain? So I'm not going to give you the precise mathematical definition because it requires a bit more preparation. I'm going to give you the idea, and that's going to be sufficient for our needs. So a simply connected domain, a simply connected domain is a domain, and this is completely general, but in our discussion, the examples that we're going to discuss, we're going to discuss separately domains in 2 dimensions and in 3 dimensions, because it's going to be somewhat different, is a domain in which there are no holes that pass all the way through it. So just to emphasize that this is the intuitive notion, I'm going to add these here. Excuse me? This works for both. Let me do some examples and explain. But again, this is not the precise mathematical definition. Okay, so what do I mean? There are no holes that pass all the way through it. So in 2 dimensions, in 2D, so we're looking at a planar domain, a domain in R2. What does it mean that there are no holes that pass all the way through it? It simply means that there are no holes. Okay, so for example, the disk is simply connected. Let's call it SC for simply connected. Okay, there are no holes at all. Versus, if you look at a ring, this is not simply connected because there's a hole. Okay? Now, in 2 dimensions, that's as complicated as it gets. And one important thing is that when you have a simply connected domain, the importance in terms of what we want to do with these domains, when you have a simply connected domain, and you take any curve sitting inside the domain, any simple closed curve inside the domain, that curve is going to be the boundary of a domain which is contained in your original domain. Do you see that? Okay? So if you take any closed curve, any simple closed curve, inside the domain, so this entire thing is D, and now I'm taking a curve gamma, and I cannot call its interior gamma because its interior D, because D is already the entire thing, but I can still call it some name, so let's call it E. So the curve is the boundary of some region. Gamma is the boundary of E, where E is contained inside D. Do you agree? And this does not happen necessarily if your domain is not simply connected. So if you take a curve here, depends which curve you take. So if you take this curve, for example, if this is gamma, then everything is fine, right? The interior of gamma is the boundary of a domain which is contained in D, right? But you can find a curve, for example, this curve here. If this is your gamma, then gamma is not the boundary of a domain contained in D. Do you agree? And there's nothing you can do about it. If you try to make gamma the boundary of some domain, that domain is going to go outside of D because of that hole. Clear? Everybody? Okay, so maybe let's write that. For a simply connected domain, any, or in a simply connected domain, any simple closed curve is the boundary of some, let's add letters. In a simply connected domain D, any simple closed curve gamma is the boundary of some domain, of some region E, which is contained in D. Okay? So here everything works, here everything works as well, but here there is no such E because of the hole. Is this idea clear? This is the simple version in 2 dimensions. It gets more intriguing in 3 dimensions. Is it clear? Everybody good? Okay, so let's move up to 3 dimensions. Let's move up to 3 dimensions. And let's look at some examples. So in 3D, so let's look first at a sphere. So the domain is now 3-dimensional. Suppose the domain is a sphere. Not a sphere, a ball. Sorry, 3-dimensional, solid, a ball. So to emphasize that it's a ball, let's do this. So this is a ball in 3 dimensions. Suppose I take, first of all, you can see that there are no holes, right? And suppose I take any closed curve. I'm trying to see if that phenomenon, which is what we care about, does it hold here as well. So this is simply connected. There are no holes that go all the way through. Let's take some simple closed curve gamma sitting inside D. Is it true that gamma is the boundary? I want to redraw gamma to emphasize that gamma is now not planar. All of this is happening in 3 dimensions. So think of gamma like this. Okay, I don't know if this is gamma. Can you imagine a rubber band sitting inside the ball? Okay, and you can see that this gamma is the boundary of some region inside D. Do you agree? And that's going to be true for any gamma you try and take, right? So this is simply connected. Let's look at another example. Let's look at an avocado. So here's an avocado. But I'm only going to look at the part of the avocado which we eat. Okay, so inside here, I'm going to make a hole. Okay, and our domain does not include this hole. Okay, and everything is 3-dimensional. How will we emphasize that? Okay, so we're looking at a three-dimensional avocado in which, in some magical way, the inside, the pit, was removed. Okay? This is our domain. Let's figure out if it's simply connected. Okay, so it doesn't have a hole that goes all the way through. It has a hole, right? This is a hole, but the hole doesn't go all the way through, right? Now, let's look at a gamma and see if we can say that gamma is the boundary of some surface inside this avocado. So if we take gamma here, here's gamma, that's not an issue, right? Here's a surface for which gamma is the boundary. Do you agree? What if we take a gamma here, around the hole? Do you see this gamma going around the hole? Is it the boundary of a surface contained inside D, inside the avocado, inside the greenish-yellow part of the avocado? So you're doing this. Why not? There is a hole, so it is. I can't see my face. Well, you can't see his, but you can at least see me imitating him. Okay. Watch this. Ready? Here's a surface for which gamma is the boundary, okay, for which gamma is the boundary, lying inside the avocado. Ready? Ready? Sure? Here goes. This is the surface. Can you imagine it? It's kind of an umbrella sitting here. So it looks like this. This goes behind. Can you understand what I drew here? And this surface, we made the surfaces red, so let's do it in red. I don't know if you can imagine this. Okay, so this was our original gamma. This is gamma. This is the simple closed curve. And this is the surface in red, this thing. This red thing is the surface E, for which gamma is the boundary, and it lives inside the big avocado. D for avocado. Clear? And do you see that we can do this for any closed simple curve gamma? Even if it seemingly goes around the hole, we can always find a surface that also goes around the hole and fixes things. Is that clear? So this domain D is simply connected, and it has that property. This is the property we're interested in. Clear? So what would a domain in 3 dimensions that is not simply connected look like? So for example, a cylinder. A cylinder is not simply connected. So if you take an infinite cylinder, okay, and it has to be a cylinder with volume. How do I draw that? Oh boy. Let's think of the entire space R3 minus a cylinder. So this is the cylinder itself, right? So I'm taking the entire space R3 minus a cylinder. Is this how you spell cylinder? This looks so wrong. 1L? The Y's and the I's are in the correct place. So our domain now is everything outside here except the cylinder. The cylinder is the hole that goes all the way through. Okay? Now if you take a gamma here, here's gamma. This is gamma. It's in R3 and not in the cylinder, but it goes around the cylinder. There's no surface, no region E for which gamma is the boundary such that the region is inside our domain. So this is D. D is this. Is that clear? You can't go around this because this is an infinite cylinder, right? This continues in both directions infinitely. It's an infinite cylinder. It's a hole that goes all the way through. Is that clear? Okay. And let's look at another example, a bounded example, which is not simply connected. So this is not simply connected. Here's another example. Look at a donut. So here's a donut. Can you imagine a donut? What I'm trying to... Okay, so I'm looking at like the inner part of a tire. Okay, I don't know what it's called. A donut. So there's a hole here. See, I can put my hand through here. See it? Goes all the way through, right? This is not simply connected. The formal mathematical name for something like this is a torus. That's what it's called, a torus. Why is it not simply connected? First of all, there's a hole that goes all the way through. Now let's think about it in terms of these curves. If you take a curve that goes around the hole here, this is gamma, you're again in the same problem. If you want to close it with a surface for which gamma is the boundary, that surface is going to have to go outside of the donut. Does everybody see that? Okay. So is this notion clear? Is this notion clear of what is a simply connected domain versus a non-simply connected domain? Okay. So the property that we wrote previously, I want to look at it just for a second again. The property that we wrote previously, we wrote it on this board, but it extends to 3 dimensions. In a simply connected domain, any simple closed curve gamma is the boundary of some region which is contained in T. This is what we're going to need. This is the property that we're going to use when applying this notion to what we need in calculus. Okay, clear? Now I want to just add one tiny remark. For this combined statement of simple closed curve we discussed in 2 dimensions. We said it's a curve that is closed and does not intersect itself, well, except at the end point where it closes, right? In 3 dimensions, this notion is a bit more complicated, so we're also not allowing, in a simple curve, does not only not allow self-intersections, but also is not allowed to be a knot. So this is what we call a knot. I drew it in advance because I'm not good at drawing knots. So this is what we call a knot. So these intersections mean that the bold one goes in front and the broken one goes in the back. Okay? So if you think of this, if you think of a string that would look like this, it doesn't self-intersect, but it's not... You can't unknot it, okay, without cutting it. Okay, is that clear what I'm saying? Okay, so if you would try to move this here and move this here, and you can actually take a string and play with it, you can't unknot this, as opposing to maybe something like this, which is fine. This you can unknot. It looks like there's, again, an intersection here, but you can easily do this, and then it's just a good old unknot. Clear? Is that notion clear? So this is a whole subject in mathematics and its applications. We're not going to go into it. I'm just adding a remark that a simple closed curve cannot be a knot. Okay, that's included in the reason is that for things like this, it's hard to say what a surface for which this is the boundary would look like. Okay, and we're not allowing unoriented surfaces and all kinds of terrible things like that. Everything is nice and cool here. So, questions? Okay, so now we know what simply connected domains are. And now we can go back to discussing conservative fields and seeing how they relate. And it turns out to be an important notion. So that's going to be in the next clip.